So Kai did a great talk talking about data mesh in general and where data analytics meets data in transaction style, right? So this talk will focus more on the transactional aspect of things like business and OLTP style. And, you know, moving to microservices architecture for the business side of things is really not simple, but when you want to do it with event-driven style, architecture is even more challenging. So my name is Natan Silnitsky, and I'm a backend infrastructure team lead at Wixs. And for the last 4 years, I've been developing messaging and event streaming infrastructure on top of Kafka for our microservices at Wixs. And today I want to share with you the story of how we adopted event-driven architecture for our more than 2,500 microservices in production to handle our growing scale, ever-growing scale, and all the challenges and issues that we faced, and the lessons that we learned along the way. But first, a few words about Wix. So Wix is a powerful website building platform for all skill levels, from just creating a website completely automatically with a few clicks of a button, to a custom bespoke design that an agency builds for you with all the minute details that agencies know best how to achieve. And while you can manage your online presence, you also manage your business online. So from building your schedule and bookings for your yoga and Pilates studio to sophisticated tools like third-party drop shipping. And all of this massive scale brings us to quite impressive numbers, I think. So around 1 billion unique visitors visit the Wix platform every single month. And we process around 500 billion incoming HTTP transactions every single day, and around 70 billion Kafka messages. Again, it's from users and users of users visiting our sites and interacting with our sites. And we do more than 600 changes to production every single day. And like I said, we have around 2,500 microservices in production, so I know it seems like a lot, but trust me, we really need each and every one of them. I know it's quite surprising. And so most of them are indeed in this event-driven architecture style. So it allows us to have better scaling in terms of our plethora of use cases and flexibility, but also we introduce a lot of resiliency and fault tolerance to the system when we have this kind of architecture. But we have faced several issues along the road to fully adopt the event-driven architecture. So this is what the talk focuses on. Specifically, challenges like producing message failures, like failing to produce a message to Kafka, which can cause a lot of issues. Processing events out of order or duplicate processing, and it can cause data inconsistency issues. Sending large payloads, which can break down at some surprising point in time and cause havoc. And troubleshooting production in general, because we have so many events running around this enormous system, and it's really hard to keep track and find bottlenecks and stuff like that. So all of these challenges we successfully handled, and the more tools and patterns we provided for developers at Wix, the higher rate of adoption of event-driven architecture became. But what do I actually mean when I say event-driven architecture? So let's briefly touch on that. We also, Kai mentioned a few of the points as well. So when we talk about communications between services, I'll keep an e-commerce example so it will be easy to follow throughout the talk. So we have the cart service. We want to manage the items that we put into, a shopper puts into the cart because they may purchase them. And that needs interaction with catalog service, which manages the products that the store provides. And we have the user service, which will manage all the registered users and also information on guests. And also inventory, of course, because we want to keep track on if these products are in stock. So if we look at a more traditional request-reply style communication, so we have the cart service needing information from catalog users inventory. So it will use maybe HTTP, REST, or RPC. And then we may run into issues when we go up in scales of throughputs. So first of all, we know that we are encapsulating the database behind the services. This is like one of the main pillars of microservice architecture. So that means that when we gather the information for the cart service, it will need to go one by one for all these services and fetch the data. So that means we get a bottleneck and slow processing. And maybe one of the services now, the database is really slow for some reason, so it will be even slower. So one solution here, we can put caching in the cart service, and it will allow us to gain the information much faster. But you need to decide about the invalidation strategy. When is data be considered stale? And invalidating the data is one of the hardest engineering challenges, as we all know. But it is possible to solve this issue. What about network reliability? So you may have issues actually reaching one of the services, and could be some failure. It could be unavailable for some reason. And in that case, you really face an issue, especially if you have a cascade of like a chain of requests. Like the cart requests something from the inventory service, and then it needs something from the delivery service, et cetera, and you get to a chain where the last service has some issue, and then it propagates all the way back to the first service, and it takes time to understand it, timeouts, timeout, and so it can really bog your system down. Sorry? Yeah, so you do have mitigations for such things. First of all, you have, for these cascading failures, you can introduce circuit breakers to avoid having the issue spread out and like infect all your system. And in case you have some failure, you can add retries and try again. But it's like, if you do this with RPCs or REST, it's really hard to set it up easily, globally, for all of your services to work as expected to all kinds of use cases. So it's quite a tricky thing to do usually. And so while it's possible, it's a bit tricky. Okay, so if we compare it to event-driven style, so we actually reverse the roles, right? The catalog service now produces a product updated topic event to Kafka, and then we have the Kafka promise of much of great performance and reliability, so we can trust that. And then the cart service, completely decoupled, like I mentioned, from the catalog service. It can consume the events of product updates and update its own database. And so what does this decoupling give us? So if cart service is unavailable for some reason, there's some issue, the catalog service is not affected. It can continue producing the events for other consumers that are interested. And once the cart service comes back online, it can start reading the events right where it left off, and no impact and no event will be lost. So how do it achieve it? Because it has this append-only log that Kai mentioned, and it commits, this specific consumer commits where it last successfully processed the event. So no matter what happens, it will be able to continue and not lose any messages. So event processing is guaranteed. So you get great reliability out of the box. So now I want to deep dive into each of the issues we faced with this kind of architecture. But it's important to note that I did like a streamline of the timeline, linear timeline, just to make it simpler to track. But of course, a lot of things happened in parallel throughout the last few years. And I'm focusing on e-com example, again, just to make it easy to track. But the issues we faced came up from all kinds of products and areas of Wix. So now that we talked about that, we can do the deep dive. So around 2016, we really started looking earnestly at utilizing Kafka as our event-driven engine. And e-commerce was one of the first services that there was a rewrite. They chose microservices, and issues began to happen. The cart database and the cart service, it became obvious that data did not reflect the actual catalog. So product prices, for instance, were not getting updated to the cart database. So carts were not showing the right prices. So that can really be a big problem. So the team did investigation together with our infrastructure team, and we came up to understanding that actually the catalog service sometimes failed to produce the events of product updates to the broker. So it could be a network issue, something like that, which means that the cart service will not get these updates and the cart database won't be updated. So the challenge here is how to deal with producing message failures. And more specifically, we want to make sure that we update the database and publish the event in an atomic fashion. So both should happen or none of them should happen. We decided that we're just going to solve the symptom, and we're going to introduce a resilient producer that in case that Kafka is not available, will produce the event to S3 that was mentioned a few times before today. And we then have a dedicated healer service that polls continuously periodically from S3 and then will produce to Kafka by itself. So then we get the extra reliability as a fallback in case some issue is getting us not be able to produce to Kafka. So this resilient producer is actually part of a more broad library that we offer Wix developers. We call it Greyhound. We also open sourced big chunks of it. So Greyhound offers our developers a way to simplify their event-driven style development. Greyhound Producer wraps Kafka Producer, and Greyhound Consumer wraps Kafka Consumer. And other than Resilient Producer, it also provides a higher level of parallelism, parallel processing for each of the Kubernetes pods, and also batch consumers. So in cases where you have the ability to process events in batches, it's really much better performance if you do it in batches. All kinds of consumer retry strategies. So not only making produce more resilient, but also consume. So you can do exponential backoffs and retries, non-blocking retries, blocking retries, and stuff like that, and other features that I mentioned towards the end of the talk. So around 2018, we had Greyhound Resilient Producer and the consumer retries. So developers had more confidence in utilizing Kafka for streaming these events between the different services and not losing anything in the process, and making sure data keeps getting to the relevant databases and stuff like that. But once we introduced the resilient producer, we solved one problem, but we gained another one. And that is out-of-order processing. So if we take a look at what happens when a resilient producer comes into action and does the fallback, is that maybe events will become out of order. So maybe a store owner decided to introduce a discount, but they changed their mind really quickly. And for a temporary amount of time, the network didn't work. So the introduced discount event came to the healer service, but the removed discount, the traffic, the network came back up, so it did get to Kafka. And at the end, the cart service will first get remove discount event and then get the introduce discount event afterwards, which is a problem. So how do you deal with out of order processing and duplicate events processing? That's the second challenge. And what we actually did here is we introduced a revision ID. So each and every one of the entities that is found for these events now has another revision field. And so the events include this revision ID, and we actually store it inside the database in the schema itself. So the product price in the cart service has the current version. So it knows to actually ignore if it gets version 11, it will update the database, but then if it will get version 10 after version 11, it will actually discard it because it's older than what it currently has in the database. And of course, you must keep not like have delta events for what is the difference from before. You actually need the absolute values. Otherwise, you won't be able to discard events in the middle. So you need to keep your entities with full information so that the database can update. Now, another way that you can mitigate out-of-order processing in this scenario is using Debugging connectors. So Kai mentioned change data capture. And so these connectors are listening to the database bin logs. So like Kafka, databases also have like append-only commit logs. So that can be utilized, right? And you can listen to that. So the Debugging connectors listen to that in all kinds of databases and is able to stream it to Kafka. We decided not to use that for our mainline event streaming because the Debugging produces an event that is a bit low level for our needs. We have like higher level domain events abstraction. So if we use Debugging, we'll need to translate all the events to our higher level domain event format. So that's like duplicating all the traffic and introducing more complexity. So we noticed that like using the Greyhound resilient producer was just good enough for us for our use cases. So currently we decided to stick with that and not switch over to Debugging, but we do use it, of course, for database migrations and for other use cases. Cool. So our troubles didn't end there. We also ran into issue with inventory service and its database. The data there did not reflect the actual inventory. We noticed that it actually has a lower amount of stock than there actually is in the warehouse sometimes. So the risk is, of course, to lose potential customers because they will get an out-of-stock alert while there actually is still a lot of stock left. So after investigation, we found that the problem was duplicate processing. How so? The inventory service listened to payment completed events and successfully updated the inventory database and decremented item 1, item 2 from 9 to 8 and from 5 to 4. But then it also, for the same event, it needed to do stuff with the delivery service, and something failed there. No worries, we have Greyhound automatic retries, and it just processed again, right? That's good. Well, in this case, there was no protection, and the inventory service again updated the database and decremented again for the same event. So there was no idempotency. The inventory service did not have idempotency, meaning that no matter how many times you do the processing for the same event, you won't change the state again. So how do we solve that? For a lot of our events, we actually attach a transaction ID, a dedicated ID that is found for each event. So here, it's not actually attached to the entity, like the payment. It's attached to the events. So then the inventory service keeps this transaction ID part of its own schema. And then it's like safeguards, and it can deduplicate and say, oh, wait, I already got and processed this event, so I'm going to ignore this second attempt. Great, so we introduced revisions and transaction IDs inside our schemas and formats to safeguard against out-of-order processing and duplicate processing. Now, the third challenge is about producing large payloads. So with our massive scale, something as trivial as a product description, which was fine to keep in storage, actually we came into the limit of the default payload amount for Kafka. So here, product updates sometimes reached over the 1 megabyte default. So the naive solution here is to increase the amount that you allow to go through Kafka. But then, if you're not careful, you can start slow down Kafka if you do like 2 big payloads, right? And like Kafka is not built to move video files around like in a massive scale, right? So, well, how did we mitigate it? First of all, we introduced compression universally, and we have several kinds of algorithms. I think the default one is gzip, but we do allow different services to change the compression algorithm if it's better suited for their use case. And of course, it's important to know that compression is better done on the Kafka level, so don't compress the data by yourself, and leave it to configure it to the Kafka SDK, because then it is able to compress data in bigger batches. So while this, of course, helped reduce the problem, it didn't eliminate failure to produce large payloads completely. So another way to mitigate it was to introduce logic on both sides, producer and consumer, that actually chunks the data. So we chunk the data and split it into chunks and then produce the chunks. And the consumer side needs to track when all the chunks have arrived, and then assemble it back and get the full event. So this was experimental, and it's quite a complex logic to do. It's achievable, but it's like too complex for the solution for the problem. So while this is used, it's used really rarely at Wixs, and most of the time you just upload the bigger payload to S3, attach the S3 URL into the payload, and then you can, when you consume the event, you can just download the bigger payload from S3.
Which format do you use? Packet? Do you use Packet?
No, it's just
because you talk about the compression. So
right.
maybe only compression is the solve of this. Maybe because you have like many formats like JSON, JSON, Packet, and you save it to S3. So when you save it to S3, you have like a network bandwidth and
right. I'm not sure I follow. Our schema is like protobuf based, but protobuf JSON based. So just you serialize 2 bytes and you can like save it anywhere. But I'm not sure I follow the question.
Because like JSON is like epic. So like
you mean like?
You have anti-JSON, so it without the spaces, and you have a Packet. So.
Okay. Yes, we're actually considering these days switching to a binary encoding. But usually I think the compression is good enough for like squeezing the entropy here as much as possible. But I guess no matter what encoding you have, sometimes you will reach limits here anyway. Yeah. Okay. Cool. So back in 2020, we added compression by default and added like the patterns how to solve large payloads. And then we come to the last challenge of how to debug, maintain, and fix production issues when you have such a massive event-driven system like we do at Wixs. So not like events flow around these thousands of microservices, and it's really hard to keep track. And also, if you start to have like a bottleneck somewhere, and you have to fix it quickly, like not immediately, like with request reply, but still you don't want a lag to build up, consumer lag to build up too long. So our infrastructure team got, throughout the years, a lot of questions and requests. How do I search for a specific Kafka message? So we built our own custom control plane for Kafka. And one of the first views was the ability to stream the events. So you put the topic in and which cluster, and you can decide from which time period you want to look at the events, or maybe you know partition offsets. Usually you don't. And the most importantly is filtering by the key or the payload or the headers, and hopefully find the exact event that you are looking for. And another really common question is, I got an alert that there is consumer lag. How do I investigate it? How do I know how to fix it? So we built another view specifically for lag investigations. And here you actually can see the lag. You choose a topic, and you can see all the consumer groups for this topic. You drill down for your own consumer group, and you see which partitions have the increasing lag. And you can actually click and see the last message that is probably stuck and causing the lag buildup. So it's actually the first message that is not committed yet, right? And you can view it here, and maybe you can fix the bug or something like that, hopefully. And then GA, and then the lag will go away. And of course, also with such a big system, something didn't happen, but why didn't it happen? I mean, I'm lost, please help me. So that's like questions from a few years ago. Since then, we introduced a lot of for matrix monitoring and logging, a lot of extra metadata and context. So we put in our Kafka record headers request IDs, user IDs, and we also then write it down to our monitoring infrastructure. And then all of this information propagates along Greyhound producers, consumers, and is available for all services and all of our monitoring infrastructure in tow. And so it's propagated throughout the system. And what this gives us is first the ability to see which services actually interacted with this event. So you get this picture. And because we started using the OpenTelemetry protocol, we actually get nice breakdowns of not only which services interacted with the event, but how long it took them to the interaction, breakdown how long it took with the database part of event processing and producing, etc. So it's really, really helpful for tracing. So we continuously improve our tooling that we provide Wix developers. We also provided a way to skip and replay events seamlessly. You don't need to stop any consuming. You just click in our control plane, and then the service will restart, and Graham will say, aha, I need to start from a previous offset or a forward offset, and this way we are enabled to skip or replay events. So to summarize, Wix developers have embraced event-driven architecture using all the tools and patterns that I've mentioned and more. And meeting all these challenges made our microservices more decoupled, resilient, and scalable that event-driven architecture gives us. But we also try to keep the complexity part as low as possible, and of course, data consistent, because it's not a trivial thing to do. And this talk actually originated from this blog post. So I put all the slides on SlideShare, so you can check out later all the links. So you can check out the blog post if you want more deep dive on this case study. And if you're interested in how to do a migration of your on-premise to cloud service, and maybe we also switched from a single cluster to multi-cluster. So all these like advanced operational side of Kafka. If you're interested in that, I gave a talk in DevOps. And if you're interested in learning more about ground features that may help you with your microservices, then you can check it out here. And I put the slides on SlideShare for you to check. And I gave a lot of previous talks, and they're all found on my websites, and also a lot of other relevant blog posts around Kafka and event-driven architecture. And you can also follow me on Twitter and LinkedIn for updates on what we do at Wixs around these topics as well. So thank you very much. Yeah.
So the ground, I don't know what is ground. I just read it on GitHub. You have a DLQ per topic.
Sorry?
The header service, right? It's like
Yeah.
DLQ, then the queue.
So
DLQ per topic. Why you just like move to S3 and then to the header?
okay, so we do have a DLQ pattern. We have reach-write topics, and these reach-write topics allow to have non-blocking reach-writes each in its own time period. And if all this fails, it will go to a data queue, and then you can manually investigate. But that's on the consumer side. For producer side, we have automatic healing. So in case there's some temporary issue and you can't reach Kafka, so you can always fall back to S3. And guys, if you can keep quiet for a second, we're trying to answer questions here. Thank you. We see it from time to time. You know, like in Kubernetes, pods start up, and the network, some reason for this machine is not working, and Kafka is unavailable, and or something like that, or some network issue. So because we guarantee that we find it in S3, no matter when we reach Kafka back, we know that we eventually will going to produce the events. Any more questions? Yeah.
How you choose between these three ways to handle large payloads? Is it manual choice, or you build some automated solution?
It's a manual choice. We have like guidelines that we offer, and so compression solves some of the cases, and if it doesn't, so usually you'll go with storing to S3, and not only S3. We are streaming events throughout the microservices, right? And some of the events, they all come from the microservice database, usually. And there it's stored. So it's sometimes quite large. And you can say, OK, just here's the ID of the entity, and you stream the event. And if you're interested in fetching the information, because you're filtering, not all events are interesting. You do filtering, but if you are interested, then you go back to the service and query it. So that's another alternative, not only S3. Yeah. Again, please be quiet there. I can't hear.
Why not just open a stream and say I didn't finish streaming yet, and then do just the consumer waiting for the then just do something with the data. I don't think you need to upload it to S3 and then in the consumer calling from S3 and then.
You mean like choosing a streaming way? Yeah, there are.
Video. People doing it with S3, video streaming.
Oh.
You're watching the video.
Yeah.
On YouTube, you're getting the bytes per every 1 minute, for example, something each byte is 1 minute of the data. So why not doing something like that?
You mean like bypassing Kafka? You mean?
I mean that you can just stream the data, not everything together. A bit of bytes.
Yeah, sure. So it's kind of like the chunking I mentioned, I think. Well, at the end of the day with Kafka, if you want to stream it through Kafka, you have to like put it in chunks. So that's a valid approach that you can do. You have like HTTP streaming that you can utilize as well for S3, but I showed here like something that can be surprising. We didn't decide to limit the description of the product, and some customer decided the entire product catalog. They really like to write content, and they exploded it, and it was really surprising. So now you're kind of stuck with it, and what do you do with it? So. So you can go with the chunking route, you can go with streaming to S3, definitely, both. Any other questions?
Have you had a situation with flooded messages that you didn't manage to control?
So,
like you've got so much messages that no consumer took it and it was stuck in the middle of production?
right.
Cleaned it.
Well, so of course, because of the decoupling here, usually the problem is very isolated. So if like a producer is going crazy, like of course stuff like this happens, but at the end of the day, there is like a limited amount of partitions. So as long as you don't explode it with the amount of partitions, it's hard to like bring Kafka down or something like that. And if you go with Confluent Cloud, I know they have the ability to introduce quotas. So we're in the process of breaking down our connections to the Confluent Cloud clusters to have identity per service, per microservice. And then we're thinking about maybe introducing quotas to limit the effect on like DDoS attacks and stuff like that. But all of this will always only be isolated usually on the producer side and won't affect the consumer side because
Sure.
You can limit it there.
This is the nature of the problem.
Yeah. Hope I answered. Anything else?
The last one.
Yeah, okay. Last question.
Guys, I have no idea what I'm asking about, but I want to ask anyway.
Okay.
I'm curious, what is your outlook, what is your thoughts on using AI to control such huge ecosystem of microservices, maybe in the future?
Dear ChatGPT, please write me. Please give me a great event-driven infrastructure for Wix. Well, it's a good question. I'm sure I don't know what the time range, but maybe my job will be obsolete in some point in the future. But I guess it can definitely help in finding patterns and like finding irregularities like misusages and stuff like that, and maybe offer solutions, maybe even do auto-healing by itself.
Observability on steroids.
Yes, like better observability and better auto-healing. Like if some malicious attacker is attacking your system, for instance. But other than that, you know, it's more like write me a microservice, and it should connect to Kafka and should connect to Postgres, and right, and so. But about how to do the infrastructure right, I guess that's more on the cloud side of things, and I get there are a huge amount of opportunity there. It's exciting times for sure. Definitely. Hope I answered. Thank you so much, everyone. See you then. Thank you.